So the topic of my presentation is the use of propylene carbonate in Suzuki-Miyaura reaction. In 1998, Anastas and Warner put the basis of the Greek chemistry by formulation these 12 rules. I want to mention the most important, which are, in my opinion, the prevention, the atomic economy, safer chemical synthesis, safer chemical design, use of safer solvents and auxiliary, if possible, energy efficiency, possible green catalysis, real-time analysis for pollution prevention, and last but not least, accident prevention. So in 2060, Alder and co-worker published in the GlaxoSmithKline Sustainable Solvents range. And as you see in this table, the propylene carbonate, it's thought to be a green solvent because it's synthesized by Ansel and co-worker by assimilating carbon dioxide in propylene oxide in the presence of different catalysts. So it's a polar aprotic solvent with very high boiling point and medium density. In 2008, Xiao and co-worker published that this carbonate ring system can be opened at elevated temperature and in the presence of very strong bases. And the product of this reaction will be the propylene glycol. So our aim was to use this green propylene carbonate solvent in the Suzuki-Miyaura cross-coupling reaction, which is a reaction between the vinyl-aryl, hetero-aryl, halogenated, triflated or fluorsulfonated compounds with different alkyl, alkenyl, aryl boronic acids in the presence of palladium catalyst and of course of base. So in this manner, a new carbon-carbon bond is formed. The application of Suzuki, one of the application of this Suzuki-Miyaura reaction can be seen in the slide because Larsen and co-worker in 1994 synthesized the losartan. The structure can be seen here, which is an angiotensin II receptor antagonist, starting from this bromophenyl derivative in the presence of orthopetrazolyl boronic acid, and they use as catalyst palladium acetate in the presence of triphenyl phosphine. The base used in the reaction was potassium carbonate, and as you see, they needed a mixture of solvents in order to receive in enough high yield the losartan product. The solvent mixture was containing water, tetrahydrofuran, respectively diethyl malonate. So our aim was to check the applicability of the propylene carbonate in the Suzuki-Miyaura cross-coupling reaction. For this purpose, we have three different iodo heterocyclic compounds as starting material. The first two, I mean the 2-iodopyridine, respectively 4-iodopyridine, are commercially available, while the last one, this 6-iodopyridazine 3,2-H1, was synthesized according to the literature given in the slide, starting from the commercial available 3,6-dichloropyridazine. The first step was a simple nucleophile substitution achieved in the presence of hydrogen iodine. And after that, the diodo product was hydrolyzed under basic solution, and in this manner, we were able to synthesize in good yield our last starting material. So these three different iodo heterocyclic compounds were reacted with four different boronic acid. The first one is phenylboronic acid, following is 4-fluoroboronic acid, biphenylboronic acid with two separated benzene rings, respectively the 2-naphtylboronic acid with two condensed benzene rings. General recipe used in this type of reaction was 1 millimole from the starting iodine derivative, which was reacted with boronic acid used in a small excess. The catalyst in our case was palladium tetrakis-triphenylphosphine in 0.05 millimole. The base was 2 milliliter 0.5 molar sodium carbonate, and we use 5 milliliter high purity propylene carbonate. The reaction were run under traditional oil heating, respectively microwave irradiation, but in each case the temperature was fixed to 100 Celsius degree. As you see from the table data, we can say that 2-iodopyridine give very high yield the Suzuki-Miyaura cross-coupled product with 2-naphthyl, respectively biphenylboronic acid, both in oil, respectively under microwave irradiation. In the case of the 4-iodopyridine starting material, beside the before mentioned 2-boronic acid, we receive also enough high yield the 4-fluoroboronic acid derivatives. I forgot to say that in the case of the traditional oil heating, we monitor the reaction by TLC, and we say that it was finished when the starting material disappeared from the reaction mixture. But in the case of the microwave irradiation, because we have a closed system, in each case, we fixed the reaction time to 1 hour. But as you see, after that time, we received in high yield the corresponding coupled product. When we have a starting material, the 6-iodopyridazine ring system, and in reaction with the phenylboronic acid, we observe the formation of a side chain in more or less same proportion like the Suzuki cross-coupling, the expected Suzuki cross-coupling product. The explanation for the formation of the side product is that in the presence of base, the 6-iodopyridazine hydrogen, this hydrogen attached to the nitrogen 2, is very acidic and can be released in the presence of base. The nucleophile obtained in this manner is able to attack the propylene carbonate, and in this manner we can explain the formation of the 2-hydroxypropyl side chain containing product. We have two possibilities. The first one, that the Suzuki reaction occurs first, and only after that the alkylation will take place on this nitrogen atom. But by simple reaction, we have demonstrated that this nucleophile is more nucleophile than that one. So first the alkylation occurs, and only after that the side chain product is able to react on this iodo atom with the corresponding boronic acid. So in the case of the last starting material, in the Suzuki-Miyaura coupling reaction, we will have two products that can be seen in the following table. This is the expected Suzuki-Miyaura product, and this is the byproduct. When the 6-iodopyridazine was reacted with phenyl, respectively 2-phenyl boronic acid, both in oil and microwave, we receive 1:1 proportion from these products, from these different products. When we used the 4-fluoroboronic acid, respectively biphenyl boronic acid, in reaction with the starting 6-iodopyridazine ring system, as you see, more from the side chain product was obtained, both in oil, respectively under microwave irradiation. Regarding the mechanism of the reaction, we know that it is a catalytic cycle which have 3 different steps. The first one is the oxidative addition, followed by a transmetallation step, and the last is reductive elimination in order to form the new carbon-carbon bond. But the base has a very important role because it activates our boronic acid, and in this manner the nucleophile obtained, the boronate, will be more reactive, so increase the yield of the reaction. We have made an observation that both in homogeneous and heterogeneous phases, the nanoparticle can be formed, and we published it in this article, and it was also demonstrated by the TEM measurement. So if we compare the traditional oil heating with the microwave irradiation, we can say that in each case is better if you use microwave irradiation. But please don't forget that using the propylene carbonate as a green solvent, it allows us to increase the reaction temperature, and this is why we were able to decrease the reaction time and meantime have enough high yields. So after this reaction, we want to transport this propylene carbonate green solvent also in flow chemistry. Here you can see the schematic representation of the flow chemistry. Usual use pumps in order to introduce the starting material in the mixer, and these are connected to a tube. In the tube the reaction occurs, and the tube is connected to the heated column. In this last heated column, this is filled usually with the palladium catalyst, because in the flow chemistry we have a recyclation of all the reagent, reactant, and so on. We can achieve high yield by collecting more pure or as possible pure products. So in our case, we transport the propylene carbonate on flow chemistry, and at that time the heating medium was sand, where the tube and the heated column filled it with the palladium catalyst was put in. The starting material, the iodo compounds, remained unchangeable, but we have problems with the heterogeneous system and with the pumps, so we have to change a little bit the recipe of the Suzuki-Miyaura coupling. In the flow chemistry, instead of sodium carbonate solution, we use 1.5 milliliter from diisopropyl amine base and 3.5 milliliter high purity propylene carbonate. The rest proportion of the starting material remained unchangeable, and the sand was heated to 100 Celsius degree, so the inner temperature in the tube, respectively column, was also 130 Celsius degree. the 3 different boronic acids which were entering the flow chemistry reaction are 4 fluoroboronic acid, 2 respectively 1 naphthyl boronic acid. The first step was the optimization of the flow chemistry condition, and for this purpose we use the reactivity of the 4-iodopyridine with the 2 naphthyl boronic acid. At the beginning we use a longer tube. We wanted that the reaction mixture has enough time to circulate in this tube, and low flow rate. Of course, all the starting material, the catalyst and so on, the solvent, were introduced by a pump, but as you see, after 3 hours, the yield was moderate. So we decided to introduce in the flow chemistry system a column of 5, respectively 0.5 centimeter, which was containing the palladium catalyst. And as you see, at the same time, with the same tube, we were able to increase the yield of the reaction from 30 to around 50%. The best results were obtained with a shorter tube, 1 meter, medium flow rate, 1 milliliter per minute, with filled in column. After 6 hours, we received in good yield the corresponding Suzuki cross-coupled product. Here we can see the comparison of all the 3 methods, oil, microwave, flow chemistry, when the 2 naphthyl boronic acid was reacted with the 3 different starting material. In the case of 2-iodo, respectively 4-iodopyridine, we received the best yield in microwave irradiation. I think it was not so surprising, because these compounds are light sensitive, so in the microwave they are in dark. Okay, but we receive after 5 hours in very good yield the corresponding Suzuki cross-coupled product of the 6-iodopyridazine and the side chain product too. When the starting material were reacted with 1 naphthyl boronic acid in oil, after 2 hours, we received in very high yield the expected Suzuki-Miyaura coupled product beside the side product. And in the flow chemistry, although we need to increase the reaction time, but as you see, we have a very high yield for the formed product. The last table shows us the results achieved when the 4-fluorphenylboronic acid was reacted with our starting material. Again, the microwave irradiation, respectively the flow chemistry, gave very good results. The characterization and structure elucidation of the products was achieved by proton, respectively carbon NMR spectroscopy, but we measured also the UV absorption of the compounds beside the HPLC, respectively MS measurement. In this slide, you can see some of the synthesized compound, and which are in the red parenthesis, was first synthesized by us. Because of the presence of this free hydroxy group, respectively iodo and fluoro atom, these compounds can be introduced in order to synthesize the other derivatives. And here you can see my colleagues who work with me in this project: Aliza Dex, Jennifer Sahar, Pastor Balázs, Bogdan Dóra, Mucsi Zoltán, Hudányi Krisztina, and Mandit István. And last but not least, I would like to thank you for your kind attention.